Okay, so in section 1.2, we looked at numerically and graphically. So kind of like the concept of a function. So what does it do? And we can kind of go from there. But that usually, unless you have a really weird function or one that you recognize really quickly what it's going to do, taking a more analytical approach is usually easier. And this, I believe, is stuff that you have seen. So we're going to start by looking at some properties of limits. So what you've seen so far is that the value of the limit as f of x approaches c does not necessarily depend on the value of f at x equals c. So, you know, if I plug in c just because I get out 5 doesn't necessarily mean that the limit is going to be 5. However, a lot of times it does happen that the limit is exactly whatever f of c is when you plug it in. And so these are the best kinds of limits. This is what you hope for because you can just figure this out by direct substitution. We consider these to be what we would call well-behaved functions. They do exactly what we expect them to do, and they're also continuous at that point C. And so continuity is something that we'll talk about in the next section in a couple of days. But like I mentioned yesterday, continuity is a really big concept in calculus, and that's something that we're going to continuously be coming back to throughout the year. So here's just some of our foundational limits. And guys, if this is review for you, then you can skip backwards and forwards on this video, go straight to the assignments, just kind of figure out what you need. You know, this is a college class, so you can work ahead at whatever pace. You can start at the problems, refer back to this later as you need to. All I care is that you know the information when it comes time to show me that you know the information. However you get there, that's up to you. Okay, so some basic limits. C is going to be just any real number, and so is B. And then n is always going to represent a positive integer in this case. So if I want the limit of B, the limit as x approaches c of b, so that's the limit of a constant, it's going to be equal to that constant. So the limit as x approaches 4 of 10 is just going to be 10. Now, if x is an unknown, if I have the limit as x approaches c of x, I can substitute in c, and the limit is just going to be c. And then for any function that's sort of in this polynomial form, the limit as x approaches c of x to the nth power, remember x is a positive integer, so we're not talking negative exponents or anything like that here, is just going to be whatever c to that power is. And this all sounds really abstract when you look at it in these definitions, so let's look at these examples here. So example A is an example of that first basic limit property. So the limit as x approaches 2 of 3, this is trying to let me write on it, but the wheel is still spinning. So I'm going to pause the recording until it starts working. Oh, just kidding. As soon as I said that, it just needed a threat, I guess. Okay, so the limit as x approaches 2 of 3 is just going to be equal to 3. This was the b in this case from Theorem 1.1. Number 1. Number 2, if I want the limit as x approaches negative 4 of x. Now notice that's a negative 4, not 4 from the left. If it was 4 from the left, the negative would be up kind of like an exponent. And so here we just plug in, and so we get negative 4. That is what the limit would be equal to. And then lastly for c, that's that third property there. The limit as x approaches 2 of x squared is going to be equal to 2 squared, which is 4. So those are your real basic limit properties. Those are pretty easy to work through. Okay, now here's some properties of limits, and these are really helpful when we get to the more complex functions because we're able to break them down. So again, b and c are going to be real numbers, n is going to be a positive integer, and then f and g are going to be functions with the limits as shown here. So the limit as x approaches c of f of x, we're going to call capital L, and the limit as x approaches c of g of x, we're going to call capital K. So you can multiply by a scalar, which in this case b is just going to be any real number. So if I have some function f of x and I'm multiplying it by b, then the limit is going to be b times L, whatever the limit is if you ignore that constant. And we'll see some examples of this on the next page. But for me, that one is kind of hard to visualize. So here's an example. What if I wanted the limit as x approaches 2 of 3x squared? Well, we just talked about x squared, so instead, if we think of just the limit as x approaches 2 of x squared, which we know is going to be 4, then we can multiply that by 3, and we see that it's going to be 12. That's how that property works. And then all the other basic operations also work. If I want the sum or difference, if I have an f of x plus or minus g of x, I'm just going to add their individual limits. So maybe that's something like the limit as x approaches c of 3x squared minus 4x. So the 3x squared is 1, the 4x is another. I can find each of their limits separately and then either add or subtract them depending on the problem. We can do the same thing with multiplying. Oh, geez. Flash flood warning. Sorry, that scared me. So you can multiply their limits if you have a product. That would be like, let's say, x times x squared. I don't know if you saw something like that. That would be the case. The quotient, we can divide them. So those are going to be your rational functions, x plus 1 over x minus 5. You can find the limit of the numerator and the denominator separately and then divide them out. And then if I have it to a power, so let's say that I had x minus 3 quantity to the third power, we could work it out that way. If you're interested in this proof, it is in Appendix A of your textbook. Hopefully you're always interested in proofs because I think they're always a good thing to see. So here is an example. This may have been the one that I just made up when I was talking about that. So if we want to find the limit here, and a way that we can kind of do this is to break this into two smaller limits. So we can do the limit as x approaches 2 of 4x squared. And really even we could break that down even further. That this is the limit as x approaches 2 of 4 times the limit as x approaches 2 of x squared. And then we want to add to that the limit as x approaches 2 of 3. This is really more an illustration of that property because really you could just substitute 2 here and you'll come up with the same limit. And that's kind of what I'm trying to illustrate here with this example. So the limit as x approaches 2 of 4 is going to be 4 times the limit as x approaches 2 of x squared, which is 2 squared, so that is also 4, plus the limit as x approaches 2 of 3, which is 3. And again, if you notice here, that is exactly what we would get if we would plug this in. We'd get 4 times 4 plus 3. And so that is why this substitution works. So we get 16 plus 3, which is 19. So that is the limit there. And that's going to be true for any of them, that you can just direct substitute the 2. And as long as you don't end up with an indeterminate form, like dividing by 0, then that value is going to work just fine. Okay? And that is what this next theorem says. Theorem 1.3 talks about limits of polynomial and rational functions. And so what it is saying is that if p is a polynomial function and c is any real number, then the limit as x approaches c of p of x is just the value of p at c. You can just substitute c and that'll work. And it is the same for rational functions. So if we look at this third example here, rather than go through all the song and dance of breaking that down using the properties, I can just go straight to substitution. So the way that we can figure this out, this is going to be equal to 1 squared plus 1 plus 2 over 1 plus 1. So that comes out to 4 over 2, which is simply 2. Now, if that was an x minus 1 on the bottom, this would be a whole different story because we would get 0 in the denominator, and then we would have to take some other kind of approach because you're going to get something that's undefined. That doesn't mean that the limit does not exist. That just means that direct substitution is not going to work for us, okay? And that, if you look at the very top of the screen here with rational functions, notice it says q of c cannot equal 0, meaning the denominator can't come out to 0 in order for this to work, okay? All right. Radicals are going to work the same. You just plug in the value of c because radicals can really take the form of x to the n, but we're expanding from n to not just integers, but also to rational values as well. And notice that this is only valid for c's greater than 0 when n is even. That's because if you do an even root of a negative number, you get an imaginary number, and we don't want to worry about that. Okay? All right. So the last thing we want to talk about, these last examples here. So the limit of a composite function says this. If f and g are functions such that the limit as x approaches c of g of x is L, so L is going to be the limit of g of x. And then, because we're doing a composition, we're going to take the limit as x approaches L of f of x. So then we want that to be f of L. Then it is going to be true that the limit of the composition, so now we're talking here, the limit of the composition as x approaches c of f of g of x is simply going to be f of L. And remember, once again, we set up here, L is the limit as x approaches c of g of x. So we have to start with g of x, figure out the limit, and then go from there. Now, the limit of a composite function, you almost have to kind of break it down. Okay, now we can do this by substitution as well, but I want to take this first example to help illustrate that theorem 1.5 there. Okay, so one of the things that you did in pre-calc was decomposing functions. So if I look at this, I can say that the inside bit here is one function, and then the square root itself is the other function. So I'm going to define my functions like this, that f of x is simply the square root of x, and then g of x is going to be that polynomial x squared plus 4. That makes this here f of g of x. If I take x squared plus 4 and plug it into the square root of x, I get the square root of x plus 4. Okay, so to illustrate this theorem, what we need to do first, good grief, is we are going to find, these videos are going to be crazy, I apologize, and you're all going to jump when you hear that noise on the video, so too bad I'm not there to see it. We are first going to do the limit as x approaches 0 of x squared plus 4, okay? And that we know we can just plug in. So 0 squared plus 4 is going to just be 4. Now, we want the limit as x approaches 4, because that was the limit of g of x of the square root of x, which is going to be the square root of 4, which is going to be 2. And that is going to be your final answer. Now, that comes out to be exactly the same if we had substituted up here, okay? And so that is how that theorem works. But we can't just assume that it's going to work that way. We have to know that we have a theorem that backs that up, and we do. So for B, we can do the same thing. We're going to take the cube root of 2 times 3 squared minus 10. That comes out to the cube root of 2 times 9, which is 18 minus 10, so that's 8. And we also get 2 on this one. Okay? So those are our limits of composite functions. Everything you're doing today, guys, is basically just direct substitution. So the last thing here is the trig functions. The limits of your trig functions, you are just going to substitute. So the limit as x approaches c of sine of x is going to be sine of c. And so on and so on and so on. So, and the direct substitution is going to work here in all of these unless you end up with an indeterminate form. So, if we just work through these really quickly, we get the limit as x approaches 0 of the tangent of x is just going to be the tangent of 0. Which at 0, the tangent is 0. For b, we're going to plug in and we get pi times the cosine of pi. The cosine at pi is -1, so we just get negative pi. And then lastly, we want the sine squared of 0, so that means we want sine squared of 0. Sine at 0 is 0, and 0 squared is also 0. Okay? So that's where we're going to stop for today. This should be just basic direct substitution. So I will see you all tomorrow, and we will start looking at some of the weird stuff that can happen.